Yeah, this means that the test failed. Remember, this does not mean that it diverges, right? We were trying to compare it to a convergent geometric series. We got this to not work. That doesn't mean it diverges. It just means that that test didn't work. And there's nothing I'm going to be able to do necessarily. Well, maybe I can tweak it. Nah, but who cares? Let's not tweak it. Let's just go to the limit comparison one instead. Let me try that one instead. Maybe that will work out a little better. So if I do the limit comparison, and I try the limit as n goes to infinity, let me do a sub n over b sub n, right? That's what I have. A little bit of algebra, flip it around and 5 to the n on top, 5 to the n minus 4 on the bottom. And I cannot split this into two fractions, right? Because there's 2 on the bottom, 1 on the top. But L'Hopital, right? I've got infinity over infinity. So this equals by L'Hopital's rule. Isn't L'Hopital's rule awesome? Okay, what is the derivative of the top? Uh-oh. What's the derivative of a general exponential function? 5 to the n. Good, natural log 5. So if you don't remember, derivative of a to the x is a to the x natural log a. In the case that it's e to the x, then it's e to the x natural log of e, but natural log of e is 1, so we don't write it. So that's the general derivative of an exponential. So that's what I just used on top. What's the derivative of the bottom? Same thing, right? Because the derivative of negative 4 is gone. So it's 1. We're done. So it converges. You see why it's so important that when we ran it the first time and the test failed, that we don't draw the conclusion that it's divergent. Because it actually is convergent. It's just our test failed. So we tried the test in the limit comparison version of it, and it actually was an easy result. All right. Are we like bordering on fun here? No response. Crickets. Crickets. All right, let's move on. 8.4. Is titled Other Convergence Tests. And if you look at our chart, we've done nth term, we've done geometric p-series, integral, comparison, and that's it, right? So 8.4 has the rest of this. And we're going to start out, not in the order that they appear there, we're going to start out with what's called the alternating series test. But before we can do that, I need to actually define what an alternating series is. An alternating series has this form. It's something like A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus dot, dot, dot forever. So you're still adding them up, but it's like you're subtracting, adding, so it's switching back and forth. So written in sigma notation, it looks like this. How do I start with a positive? If I want things to switch back and forth, negative 1 to the here n plus 1 would give me starting with positive, and then times a sub n. So keep in mind here that this a sub n piece right here is like your sequence, right? That part is always positive, and it's just the sign in front of it keeps changing. Understand? Now, you could also have, or you could have another version where you have negative A1 plus A2 minus A3 plus A4 minus A5 plus ... The only difference between the two is that you're starting negative on this one, right? So the only difference on the formula would be negative 1 to the n instead of negative 1 to the n plus 1. And that's still going to be some positive piece. So all alternating series look like one of those two, right? Either starts negative or starts positive. And it turns out that there's a very simple test to determine whether or not an alternating series converges. And it's on your table there. So the alternating series test says, I'll just cheat here, alternating series test. And I'll refer to this as AST from now on, alternating series test. It says that, if you've got some series where you got negative 1 to the n, a sub n, and remember that n up there could be n or it could be n plus 1, right? It doesn't matter. As long as it's an alternating series and the a sub n's are positive, then it converges if what? Okay, a sub what? A sub k greater than or equal to a sub k plus 1. Okay, and then what's the second thing that has to hold? Limit n goes to infinity of a sub n must equal 0. That's it. Those are the only two things you have to be able to show in order to show that an alternating series converges. So let's discuss these, and I'm going to start with the easier one first. Isn't this the nth term test? Isn't that just you taking the limit as n goes to infinity of this piece right here? Without the negative in there. Just look at that piece right there, let n go to infinity, and hope it goes to 0. Like, we used to not want this, right? Now we actually want it for alternating series. If it goes to 0, and then the second condition is this. Can anybody tell me what this condition is? This one right here.
Means that every term is bigger than the last.
I think you have that backwards. The k plus 1 term is smaller than the k term. So like, if this is the first one, this is the second one, right?
Yep.
So yeah, you had it backwards, but you got the idea. So every term is getting smaller as you move through. There was another name for that. When we were in 8.1, when we were talking about sequences that did this were called what sequence? Decreasing. So that's it. To show an alternating series converges, you just need this limit to go to 0. So you need the nth term test to give you 0. And then you also need to show that the sequence of the positive pieces right here is a decreasing sequence. If you can show that, you're done. It's nice. The alternating series test is one of those tests that's really pretty simple to employ it, right? You just show these two things and you're done. Do you recall when we were doing sequences in 8.1, the two different ways you could show a sequence decreased? There were two different ways to do it. The derivative was one of them. If we could show the derivative of the sequence was negative, that would mean it decreases. And then the other one was just to actually show that this inequality was true. So let's do an example. I'll give you your first alternating series. And let's do this. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth Yeah. Plus a seventh. Dot, 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 right? Does that look familiar? What type of series does that look like? Harmonic. That looks like 1 over n, doesn't it? But it's not. It's slightly different because of the alternating. So it looks like, start with a positive. So how about -1 n plus 1? That'll start me positive. And then just 1 over n out here. Will that create that series for me? Yes. Yeah? All right. So the piece that I'm interested in here, the only thing I'm interested in is this. This is what I'm calling my a sub n. And what I need to show now are 2 things are true. Okay? So alternating series test. Let everybody know I'm about to use it. AST. First thing I want to show, that a sub k is bigger than or equal to a sub k plus 1. I'm only using a sub k and not a sub n because what's on your sheet, they used a sub k. You could, if you want, replace these k's with n's. It's the same thing. All right, so what is a sub k? It's that with k instead of n, right? So the left side is 1 over k. Is that bigger than, and this is the question, is that bigger than this with k plus 1 in it? 1 over k plus 1. Yeah, you can cross multiply. I've been doing a lot of this cross multiplying, haven't I? And I hate that word cross multiply because it's technically not what we're doing. We're clearing fractions is what we're doing. But it seems to click with most students when I say it. So cross multiply. I have not been worried at all about flipping inequalities, have I? But you always have to worry about flipping inequalities because if you ever multiply or divide by negative numbers, it should flip. So remember, the reason I'm not even talking about that is because k is positive. Right? K is the n starts at 1. So I have not been concerned about the inequality flipping, although it's always been there in the back of my mind. Okay, subtract k, both sides. 1 is bigger than or equal to 0, and that is true. So it converges. I still have to check the second thing. So the second thing I need is to show that the limit as n goes to infinity of a sub n equals 0. So I want to make sure that the limit as n went to infinity of 1 over n, this, is 0. Is it? Yes. It converges. That's it. We're done. That was a little too easy, right? We do another one. Sum n equals 1 to infinity, -1 to the n times n squared over n cubed plus 1. Well, what type of series is this? Alternating, right? So as soon as you see alternating, then you pretty much throw out the comparison test, the integral test, the p-series, all that goes away. Because those only work for series that have positive pieces in it. Whenever they alternate, you got to go to the alternating series test or the ratio test also, but we haven't talked about the ratio test. We won't get to that today. All right, so alternating series test. Let's identify the a sub n. So what's a sub n for us? Make sure you're aware of it. Yeah, good. It's just this piece, right? That's my a sub n. That's what I'm going to be doing all the work on, right? The -1 to the n out there really makes no impact on how I'm testing things. So first thing I want to show a sub k bigger than or equal to a sub k plus 1. Oof. Now, I could do that. Let's write down what that would be. I would have a sub k, which is that with just k's in it, k squared over k cubed plus 1. Is that bigger than or equal to this with k plus 1 in there? So k plus 1 quantity squared over k plus 1 quantity cubed plus 1. And then we could start trying to like cross multiply and clear fractions, whatever, right? And I could do that. And I'm sure you would love to do that. Maybe you'll do that while you're hunting Easter eggs this weekend. But I'm going to try this a different way. The other approach to show something was decreasing was to take the sequence, convert it to a function, take its derivative, and see if it's negative, right? So I just want to do this one that way so you can see it done. So I'm going to say, nah, not today. Instead, I'm going to let f of n, a function of n, be the sequence. And then I'm going to take the derivative. I want to show that f prime of n is less than 0 eventually. So can I show that the derivative is eventually going to be dropping off, or the function will eventually drop off, right? So what is the derivative of this? What are you going to have to use? Quotient rule. So we'll do a quick quotient rule on this. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And when you look at that, your question is this negative, right? Is that negative? And that looks like a disaster, doesn't it? But let's just clean it up, all right? Let's just clean it up a little bit and talk about what we've got. So we have 2n to the fourth plus 2n distributing minus 3n to the fourth over what I hope you would agree is a positive number no matter what. Do you agree that denominator is positive no matter what? As long as n is 1 or bigger? So if I have a positive down here, I really don't even need to consider it, do I? Because the positive is not going to impact the sign, right? If the top is positive, this thing's positive. If the top is negative, this thing's negative. So the bottom has no impact. Agree? All right. So now let's continue. On the top, what does the top turn into? Negative n to the fourth plus 2n? Negative n to the fourth plus 2n. Is that less than 0? Question. I still don't know. Can you tell that the negative n to the fourth is going to start dominating at some point? But let's still try and do a little bit of algebra here. How about I factor out an n, and I'll be left with negative n cubed plus 2 is less than 0, right? Question, is that true? What about that n out front? It's always positive. So really this turns out to be this. Is this true, right? Because again, if that's positive, then whatever this sign is, that's what the whole thing's going to be. So I'm just down to this now. And I can just move the n cubed over by adding it. And that's really obvious as long as n is bigger than 1, right? This is true eventually. This is true for n bigger than 1, that's true. You could say if n is bigger than or equal to 2, but definitely n bigger than 1, we're in business. Yeah? So is it decreasing? Yes, right? Does it converge? Have we shown everything we need to show? We still need to do part 2, which is the limit, right?